Everybody. We're just going to give it a minute for other people to arrive. How's everybody doing this morning?
I'm doing well. How are you?
Good, thank you.
Just fine.
I have to warn you guys, we have some really serious winds. I'm in the Boston area. We have some serious winds right now. I'm hoping, pretty sure we won't lose power, but if we lose power, then getting feedback. Fix that.
What?
If we lose power, then I'll put an announcement later. We'll try to figure out, like, make up the time, because obviously if I lose power, then I can't get my internet isn't going to work. So bear with me if all of a sudden things go, things just stop without me saying goodbye. You'll know it's because we lost power here. But we should be fine. I just felt like I should warn you ahead of time. We're going to give it a little bit more than normal.
Yeah.
Okay. So let's sort of kind of take a stock of where we're at. So we're going to finish chapter 1.6 in just a little bit. We've basically got one more example that we're going to cover in 1.6, and then we're going to start chapter 2. We're going to do, probably we'll have time for 2.1 and 2.2. They're kind of short in terms of their chapter size and the content in them. And then I think I'll end at that point, and then if we have time at the end of class, then I'll answer questions on homework. So right now it looks like we're going to have our homework that's 1.5 and 1.6 that's going to be due on Thursday, tomorrow at midnight. So keep that in mind for what's coming up. Also, those will be the basis for our quiz on Thursday, or the quiz starts on Thursday. It's a 24-hour availability window. So keep that in mind, but we'll see how we do at the end of class today for time. And then, but I think, I'm pretty sure we're going to be able to get through 2.1 and 2.2 today. Okay. So let me just do a quick recap of where we were last time. So we, in 1.6, we're talking about higher order derivatives. So specifically, we're focusing on the second derivative, which is going to give us information about not just where we have, like the first derivative tells us where we have our max and our min values, but our second derivative tells us about those. Is this a concave down or is this concave up? We have our second derivative can do that. And then also our second derivative can give us information about where our graphs are changing from concave up to concave down. These points right here, they're called inflection points. Okay, so we did the second derivative test. Excuse me, our second derivative test from last time was, we've got our critical point, right, that we're taking a look at. So we've got this critical point. We're evaluating it. Basically, we're looking at where's our second derivative equal to 0, okay? And I can take my x value that gives me where my second derivative is equal to 0, and my second derivative test says on these values that are critical points, right? If my, oh, I see, this is our second test for inflections. I'm sorry, I'm looking at the test for inflections. So the test for inflections is where our second derivative is equal to 0, okay? Then we have to take a look at if our second derivative changes sign on either side of that inflection point. And if it does, then we're looking at an inflection point. Our second derivative test, okay, basically we take our critical point, which is where our first derivative equals 0. We plug it into our second derivative. If we get a positive number, then we're dealing with a local minimum, right? Because that means that our graph is concave up. we get a negative number, we're dealing with a local max because our graph is concave down. If our second derivative is equal to 0, then it's inconclusive. I need to do another test, okay, which usually we would go back to using like our first derivative test, okay? So remember, your first derivative test is I've got a critical point and I'm checking the slope, okay, of my, is my first derivative positive or negative on either side of that critical point. That's going to tell me that I'm dealing with a minimum value, okay? So all of these first derivative tests, second derivative tests are things that you have like tools in your toolkit for being able to take a look at and describe the nature of the function that you're working with, okay? And you will be asked to use like the first derivative specifically or the second derivative specifically as a test for behavior of your function, okay? And then other questions will say use like whatever test you want to describe this stuff, but it should be first or second derivative test. Okay, so I'm looking at my lecture examples for chapter 1.6, okay? And we're going to analyze, this is example number 4. We're going to analyze the critical points of f of x equals x to the 5th minus 5x to the 4th, okay? Let's go ahead and do that. So the first thing I need to do is I have to find where my critical points are. So I take my derivative. So I'm going to get 5x to the 4th. Now remember, I'm for those of you who recognize that I'm using the power rule when I take these derivatives, okay, which technically speaking, we're not learning the power rule until chapter 2, but when you do your homework for 1.5 and 1.6, you can use the power rule. All right, minus 20x cubed, okay? So I've got my first derivative. I'll take my second derivative while I'm here. 20x cubed minus 60x squared, okay? The wind is really heavy right behind me. Okay, so I'm going to set this equal to 0, okay? And I'm going to factor out a 5x cubed. See what I get. I get x minus 4. Okay, so I'm doing this to find my critical points on this function here. So here, I set that equal to 0. I solve for x. I get x equals 0 and x equals 4 as my critical points. Okay, these are the things that I'm going to be testing. Okay. Now, first I'm going to use my second derivative test. Okay. When you do something like a quiz or a test or whatever, make sure you tell me which test you're using, first derivative test, second derivative test, just so that I can see that you know which test it is that you're working on. Okay, so my second derivative evaluated at my first critical point. So I take my second derivative here, okay, and I plug in everywhere I see an x, I plug in 0, okay, which is going to give me a 0. So this is inconclusive. If that was our, if it was positive or negative, I could tell something, but if it was 0, it was inconclusive. So I'm going to have to come back to this point here, this critical point, and do another test on it. I'll do that test in a minute. But let's check our other critical points. So I'm going to plug in 4. So I'm going to go 20 times 4 cubed minus 60 times 4 squared. And I'm going to get 320, okay, which is greater than 0, which makes it positive, right? My second derivative is positive, right, which means that x equals 4 gives a critical point. The critical point which gives the function evaluated at 4 is a local minimum, because it means that my function itself is concave up. Second derivative positive, concave up. Okay, so this is a local minimum. Okay. So I'm going to go back to my inconclusive critical point. Okay, so since the second derivative test failed at x equals 0, I have to use a different test. I'm going to use my first derivative test. Okay. So be aware, like if you get something where it says it's inconclusive, or if it fails, you can't quite tell what the answer is, use other tools in your toolkit. Okay, we have our first derivative test, we've got our second derivative test. Okay, so that means that if x equals 0, I have to pick values of x that are on either side of 0. A little bit less than, a little bit greater than. You know, I can go as far away from 0 as I want, but I'm not going to go too far. I just want to, you know, do close by. So I'm going to take a look. So my first derivative evaluated at a number that's just slightly less than 0. So I'm going to look at -1. I'm going to plug this into my first derivative now, right? So this is going to look like 5 times -1 to the 4th minus 20 times -1 cubed, okay, which makes it 5 plus 20, okay, which gives me 25, which is a positive number, okay. So this is positive along the interval -infinity to 0, okay? Right, because this is where we're coming in here. So I'm going to take a look on just on the other side of my critical point right here, x equals 0. So I'm going to look at 5 times 1 to the 4th minus 20 times 1 to the 3rd. Okay, so this is 5 minus 20, so we're looking at minus 15. Okay, you can see I'm changing sign, right? I've got a positive and a negative, which is negative. So then we're looking at, this is negative along the interval 0 to 4. Okay. Have to be careful. Okay, this isn't going to be 0 to positive infinity because I have this other critical point here that I'm dealing with. Okay. So now I'm looking at, right, it changes sign, which means that my slope is doing something. It's positive and then it's negative as I head up to it. So I'm going to make that conclusion. So I'm going to say, since my first derivative changes sign from positive to negative at x equals 0, that means that my function evaluated at 0 is a local maximum. And indeed, I can actually, I plot this out on my calculator. Plot this out, it's going to look something like this. Right, this is my x equals 0 right there. This is x equals 4 right here. Oops, sorry, there. This is my function. Okay. Now remember, these equations, they're relatively straightforward. I can plot them out fairly easily, right? But the plot that's just for you to take a look at, like we're not grading the plots, right? But it should, kind of line up with what it is that you're seeing here too. Okay, so if one of your tests fails, right, then you can go try a different test. All right, I think it looks like I skipped the first example. So why don't we just do that one really quick? I said I wanted to come back to that one because it was not the best example. Does everybody have this before I turn the page? Go back to our first example here. This was on right, our lecture example pages. Example 1, we're going to find the points of inflection, okay, of this thing here. Okay, so first off, here's my cosine function. And right, our cosine, right, it's this ever repeating, function that does this. This is 1 minus 1. Okay. So this is our function here. Just wanted to plot it out. Okay, and we're on this interval from 0 to 2 pi. Okay, so okay, so now when I go to take this derivative, okay, my derivative of cosine is minus the sine. Okay, my second derivative of this, my second derivative of cosine, my first derivative of this, is going to be minus cosine of x. Okay. So now what I need to do is I'm going to set my second derivative equal to 0, and I'm going to solve for x. Okay, so the question I need to ask myself is, within this interval 0 to 2 pi, what values of x are going to give me the cosine is equal to 0? Okay. And we're taking the inverse cosine of 0, essentially is what we're doing. So, and I'm working in radians, so this is going to be x equals pi over 2 and 3 pi over 2. Now remember, we've limited this to just the interval 0 to 2 pi. Otherwise, I'd have to look at, multiples of pi over 2. Okay. So now, what I'm going to say is, remember, this is at the very beginning of the chapter, which is kind of why I skipped it and came back, because it didn't have a lot of details about how we solved it. But here, we're going to say our second derivative changes sign at pi over 2 and 3 pi over 2, right? So like if I were to plot my second derivative, this isn't enough work to show on an exam, but just to show you guys what it looks like. So I'm going to go this, right? So I've got these intervals, right, where my second derivative is negative, where it's positive, and then where it's negative. Okay, so my second derivative changes sign, right, at pi over 2 and 3 pi over 2. Okay, which means that x equals pi over 2 and 3 pi over 2 are inflection points. It's not enough work to show the graph, right, and say, okay, look, we can look at the graph and it's changing sign. You have to be able to show table values. Remember how we did this on example 2, we set up a whole table of an interval, the test value, the sign, what's the behavior, okay? So this was just, that's kind of why I skipped this one at the beginning. Okay, so we're kind of summarizing, kind of hand waving a little bit, and then we get into the meat of actually how we solve it. Okay. That's chapter 1.6. And I'll scan in our lecture example solutions and post them to our class page later today. Okay. You guys, I'll have this here before I take it away. Okay. All right, so let's take a look. Very exciting. We get to start chapter 2. So chapter 2.1. Okay, so chapter 2, in the beginning, we're going to be talking about a lot of different rules for differentiation. Okay. First couple of rules that we're going to talk about are power rule and linearity. Right? We like the power rule because it's a shortcut, right? We don't have to do all this limit as h goes to 0 and this the rush, and so it makes it easier for us because it's sort of like a it's a shortcut, right? But remember, the power rule isn't some independent rule that happens on its own. It's all based on our limit as h goes to 0 of f of x plus h and all that. So all that stuff that we did at the beginning of chapter 1, okay, with taking the limit and doing the definition of the derivative is where these rules come from. Okay, these are shortcuts where people said, hey, look, we're seeing a pattern here and the pattern holds true. We can just take the shortcut instead of taking the limit. But you should know that the power rule comes from this definition. Okay, it's not something that just comes out of thin air like magic. Now, also the same thing with, we're going to learn in chapter 2.2, I think the product rule, the quotient rule, they all come from our definition of the derivative. Okay, so these are all things that are going to give us shortcuts, so I have to go through the limit every time. Okay, well, let's go ahead and jump right in. So our power rule. Okay, so this is for all exponents. Right, so n is we're going to deal with, we're dealing with real numbers in this class here. So we're going to deal with for all exponents that are real numbers, we're going to call it n. So I'm going to take the derivative with respect to x of x to the n. Okay, x is my variable, n is a number, right? It's my exponent value. Our power rule says when I take the derivative, I'm going to take my current exponent, bring it down out front to multiply. I've got my variable again, and then I subtract 1 from my exponent. Okay? We'll do a bunch of examples so you can see how this works, but this in essence is your power rule. If you have a constant term in front of your x to the n already, constant term gets multiplied by the n that you're bringing down. Okay, we'll do some examples so you can see that, but this is our power rule. Don't get this confused with exponential functions, okay, which is where our x is in the exponent. We're going to deal with those later. Okay, we're going to talk about how we do that. So something like, do a couple of quick examples. I'll do it in green. These aren't officially examples in our official book, but e of z squared. This is my variable is z. Okay, and it's being raised to the second power. Now when I take this derivative with respect to z, I bring my exponent 2 down out front. I repeat my variable, and I subtract 1 from my exponent. This just becomes 2z. If you haven't already gotten into the habit of drawing your z's with a line through them, start it now. It's really important because if I write 2z, but I don't put a line through it, sometimes it'll look like 22, and I'm like, why did they write 22? So for ease of reading, make sure you put a line through your z. I take the derivative with respect to t, say for example, e to the 20. Okay, we're going to do the same thing. I take my exponent, bring it down out front, have my variable repeated, and I subtract 1 from my exponent. So then this becomes 20 times t to the 19th. Okay, my power rule. This can work with fractional exponents too. So if I've got something like radical r, don't think about this as being an exponent, which is r to the 1/2. Okay, any kind of a root. My root here, we don't write it, it's so common, but the root here is 2. Okay, so I'm going to take that second root. Now what happens is, if it's a root, my exponent is 1 over whatever that root is. Okay, so this was a cube root, then it would be r to the 1/3, say for example. So I'm going to do the power rule on this one. So this becomes, right, I take the exponent, bring it down out front, r, repeat my variable, 1/2 minus 1. You know, watch what happens. So this is going to be 1/2 r. 1/2 minus 1 is minus 1/2. I can have a negative exponent. Negative exponent just means that I'm dealing with a variable that should be in the denominator. Okay, you can write this as 1/2 times 1 over r to the 1/2. That's the same thing as this one here. We're all just writing it in the same way. Okay, this is all equivalent. And you may want to be able to go back and forth in terms of how you represent these things. Okay, whenever I see a radical, then I convert it into an exponent so I can take its derivative. You guys all set with that?
Sorry, I just have like a quick question. What happens if you have pi? How do you differentiate pi?
How do you differentiate pi? Pi is just a number, right? So, so if I've got like let's say it has to be some kind of variable. So pi, right, is like 3.14, you know, so on and so on, right? It goes on forever. So it's just a number. It's as though I were to say, so pi d dx, if I said pi times x, right? So pi is just a constant term. So that's like, we're actually going to talk about there's a constant term here, constant multiplier. It's pi times d dx of x, right? It's just a constant multiplier. So if I just wanted to say d dx, for example, of just plain old pi, which is like implying that my x is raised to the 0th power, it's like x to the 0. So I do the power rule again, right? So I've got pi, right? It's my constant that gets multiplied. I multiply by the 0 that's implied there, x to the minus 1. Well, it doesn't matter. This 0 is going to make it all 0. This is the reason, our power rule is the reason why, you know, our derivative of a constant, right, is equal to 0. Also think about like our constant is just, if I have an equation that's y equals 3, like y equals 3, it's just a flat line, right? Its slope is equal to 0. So y equals pi is also just a flat line. Okay, its slope is equal to 0. Right, so remember our derivative is telling us what's the slope of the line that we're working with. Okay, so pi is just a number.
Thank you.
Yep. All right, so our next theorem. So our next theorem is called a linearity rule. I kind of did this a little bit before when we were talking first about derivatives. So the first thing we're going to assume that our functions f and g are differentiable. They're differentiable already. Okay, we don't have to worry about that. So the first thing I'm going to do is I'm going to say my sum and difference rule. My sum and difference rule says that if f and g are being added or subtracted together, so this is for f plus g and f minus g. So I'll write it as a plus or minus. So so if my individual functions are differentiable, if I've got f plus or minus g prime, I'm going to take that derivative Then I'm going to go f prime plus or minus g prime. Okay. All I'm doing is, like if I've got this long string of terms in my equation, right? Whether it's a polynomial or it's an equation that combines polynomial with exponential with other trig and stuff like that, I'm just going to take the derivative of each individual piece. Okay, and then that's all it says. If the things are being added or subtracted, take the derivative of each piece, continue to add or subtract what those pieces are, their derivatives. Okay, I think we kind of covered this a little bit in chapter 1. All right, we've got this. The other one is a constant multiplier. Well, I kind of just touched on it when we were talking about pi, like pi times x. So we've got our constant value, c, we'll call it c. It's just a number like pi or 10 or minus 5, things like that, just a number. So if c times f, let's say f of x, is differentiable, then basically what happens is c times f, you go to take the derivative of that whole thing. That's like saying, I'm going to pull the c out, take the derivative of my function, and then multiply it back in later. Okay, we'll do examples so you can see what this looks like. But basically it's like if I've got a constant times a function, I can yank that constant out, take the derivative of the function, and then multiply the constant by the derivative later. Okay. All right, so I'm looking at my lecture examples page for chapter 2.1 now. So I want to calculate dg dt, like g of t is our function, right, when t equals 1. And I've got g of t equals t to the minus 3 plus 2 radical t minus t to the minus 4/5. So we're kind of combining a lot of different like fractional exponents here, and exponents that have negative numbers. Okay, so let's write this out. So I'm going to go d dt. I'm going to write out the whole thing here. So t to the minus 3 plus 2. And what I'm going to do is I'm going to convert this 2 to the 1/2, t to the 1/2. I take my radicals and I convert them into an exponent so I can do my power rule. Minus t to the minus 4/5. Okay. All right, now if this was t to the minus 3, so t to the minus 3 is equal to 1 over t cubed. It's helpful if you've got something like this, 1 over t cubed, to make it as a single exponent, t to the minus 3, so that you can do the power rule on it. Okay, now what's going to happen is my linearity rule says I can take the derivative of each one and add or subtract each individual piece. So let me just write out what that is so that you can see. T to the minus 3 plus, here's our constant multiplier. I'm going to pull the 2 out. Oops, sorry. dt of t to the 1/2 minus dt of t to the minus 4. Okay, just to let you know, like that's what we're doing. We're going to take the derivative of each individual piece and then add and subtract them all together. Okay, so let's go ahead and do it. I'm going to do the power rule on each piece. Okay, so now on this piece, right, I bring my exponent down out front, repeat my variable, and I subtract 1 from this. Minus 3 minus 1 is minus 4. Okay, I've got my 2, my constant multiplier, 2 times. I bring my exponent down out front. T to the 1/2 minus 1 makes it minus 1/2. Okay, I'm going to subtract. So I'm going to bring my exponent down, minus 4/5 t to the minus 4/5 minus 1, right? So let's remember our fractional rules. So minus 4/5 minus 1 is like saying minus 4/5 minus common denominator 5/5, right? So this becomes minus 4 minus 5 becomes minus 9. Okay. Now I can, clean up some of this stuff here. I can put things in the denominator if I want. So this is going to look like minus 3, the minus 4th, plus, so 2 times 1/2, that's t to the minus 1/2 minus, a minus is plus 4/5, t to the minus 9/5. Okay. So far this is our derivative, right, which I can also write like this, minus 3 t to the 4th plus 1 over radical t plus 4 over 5 times 1 over t to the 9/5. You can leave it either way is fine, right? Now what we want to do is we were told to take a look when t is equal to 1. So what I'm going to do is I'm going to substitute t equals 1 into my derivative here, because we're looking at what's the slope of our tangent line, right, when t is equal to 1. That's what we want to find out. That's why all this is happening. Minus 3 times 1 to the minus 4th plus 1 to the minus 1/2 plus 4/5 1 to the minus 9/5. Okay. So now we work it through, which is equal to minus 3 plus 1 plus 4/5. Okay, I'm just going to add things up. Minus 6. Okay. Tried to show you all the little micro steps on how we did that. Questions on what we did? Okay, great. So let's go on to our next page. So we want to, example 2, we're going to calculate our derivative x to the 0. We kind of did this a little bit previously when we were asking a question about it. So x to the 0, right? What I'm going to do, x to the 0 is like saying, what's our derivative of 1, right? Just because anything raised to the 0th power is equal to 1. So remember how we said before that was equal to a constant term? When I take the derivative of a constant, I get it equal to 0. But the reason is I do my power rule, right? So I bring down my exponent. I've got my variable, 0 minus 1. Well, it doesn't matter, 0 minus 1, because I'm multiplying by 0. But that's why our derivative of a constant term is equal to 0. Okay. All right, so let's talk about polynomials. Polynomials are fun to take the derivative of because they're pretty straightforward, right? But let's think about, say for example, if I've got some polynomial, 6x to the 8 minus 3x to the 5th plus pi x cubed, right? So there's your pi as a multiplier, pi x cubed plus 2x squared minus x plus radical 2. I've got this long stream of things, right? We usually write it where you've got the highest exponent first and going down. When you get to calculus 2, you reverse it where you go the lowest one up for reasons that you'll find out next semester. But when we want to talk about polynomials, it's helpful to think about things in terms of what we call sigma notation. Okay, so sigma just means sum, right? So I'm going to sum up all of my terms. A polynomial is just a sum of terms, right? And so what I can do is I've got let's see, there's a, let me give you the definition from our book and then we'll discuss what that means. So in case you're reading the book, then you'll see what this definition means. So we've got a definition. So we have two integers, m and n. And m is less than or equal to n. Okay, so we've got some real function b. We're not going to define it just yet, but real function b whose domain includes all integers I such that I is between, oops, sorry, m and n. Okay. Now we can say then, if this is true, then I can represent sigma notation. I can say that the sum I equals m to n. So I'm going to start. I is like my looping variable. If you've done computer programming before, it's your looping variable, right? So I equals m to n, where I begin at m and I end at n. B sub I. Okay, where b is my function, I is like each term in my function. And so this is going to look like b sub m plus b sub m plus 1 plus b sub m plus 2 plus so on and so forth, all the way up until we get to b sub n. Okay, I'm going to keep summing up all this stuff. There are formulas, you know, like, so I can represent polynomials, you know, with a given formula. How am I going to represent this b? That's part of like what you're going to be learning, right, as you go along in your engineering career, how I can turn this into a formula. As we go along, also, we can think about how we can take derivatives and integrals and stuff using just the summation notation, right? So I guess to finish writing that, example 2, we're going to enumerate. We've got this sigma notation of I equals -1 to 3 of I squared. We're going to enumerate it. So we're going to start, right? We're going to basically loop through all of our different I values. So -1, 0, 1, 2, and 3, right? So I'm counting up, right? Starting at -1. These are integers, so I increment by 1 each time. So this is going to look like -1 squared. So this gives me the formula, right? I take my I and I plug it into here. So -1 squared plus my next term up in the loop, 0 squared. This is I equals -1, I equals 0, plus the next one up, 1 squared, so I equals 1, plus 2 squared, so I equals 2, plus 3 squared, I equals 3. So we're plugging it into our formula. It's pretty straightforward. So I'm going to get -1 squared, that's equal to 1, plus 0, plus 1 squared, 2 squared, plus 3 squared. Sum all of those up. Sigma means sum, right? So I'm going to sum all of these up. I'm going to get that's equal to 15. Okay. So sigma notation, and we're kind of throwing a bunch of stuff out at you here, just to make sure that you have it so we can use it later to define stuff. Okay. So
Sorry, what does the 3 mean at the top of the sigma sign?
oh, it just means I'm going to start at, it tells me when to stop looping, right?
Okay.
So this is like a computer program, like a loop where I say, you know, for I equals 1, starting at -1, increment I by 1 value until I equals 3. So in like a computer program, we would say, does I equals 3? If it doesn't yet, if it's still less than or equal to 3, then keep looping through and doing this formula right here. If I equals 3, then stop. Like, you know, this is inclusive of 3. Okay, so use 3 as your last term and then bounce out of your loop. Right, so this tells you I start here and I end there.
Okay, thank you.
And I include, yeah, and I include those values. So sigma notation is important because I can use it actually to define a polynomial. So right, so I can say I've got my polynomial, right, I've got, oops, sorry, that's a0 plus a1 of x plus a2 of x squared plus so on and so forth, an of x to the n. Okay, this is our polynomial, right? See, you notice how I started at the smallest exponent value and I worked my way up. It's opposite from what we usually think, but it allows me to take this polynomial and represent it using sigma notation. So I can say I equals 0, n, right? I've got this a sub I, x to the I value, right? So when I equals 0, x to the 0, that's just equal to 1, a sub 0, that's this first term, plus, that's the sigma plus. When I equals 1, I get a sub 1 times x to the 1, plus a sub 2 times x to the 2, plus a sub 3 times x to the 3, so on and so forth. A sub 3 is going to be, you know, defined somewhere else. It's going to be something. It's like your coefficient terms, but it could be, you know, a function itself. It could be a formula. It could be all sorts of stuff. But for right now, we're just considering it to be a coefficient. Okay, so sigma notation is important because it's a shortcut, right? I can just say my polynomial is this, right? Instead of, you know, and this becomes really important when my polynomial gets really, really, really long. We're used to thinking of things in terms of like cubic or maybe, you know, like the 8th power, perhaps something that can fit on a line on a page, right? But polynomials can be infinite. I can have an infinite number of terms, which I'm not going to sit here all day and write out an infinite polynomial, right? So I need to have some formula that's going to help me do that. So the sigma notation is important for that. Okay. So let's use our sigma notation now to say, talk about linearity in the power rule. So let's do linearity and power rule with our polynomial and our sigma notation, which also is called summation notation. Okay, so let's go ahead and talk about that. So let me rewrite what I just put down. So my polynomial, a naught plus a1 x to the 1. I'll write out x. We don't usually write x to the 1, but I'll write x to the 1 so you can see that they go hand in hand. Plus 3 x to the 3 plus so on and so forth plus a sub n x to the n. Okay. Now, if this were like just a polynomial, right, I would take the derivative. So I'm going to do what I do with my power rule. My derivative of a constant term is 0, so that term goes away. I'm going to go my a1 times 1 times x to the 1 minus 1. X to the 1 minus 1 is 0, so the 0 is just 1. So a1 now becomes my first term. That's my constant term. Always. Now here, I'm going to bring my exponent down out front. 2 minus 1 is equal to 1. Bring my exponent down out front. Decrease my exponent by 1. Plus, so on and so forth, plus. We're going to do this again. So this is going to become n times a sub n x to the n minus 1. Okay, so that becomes our derivative of our polynomial. Right, when I have all these terms, I'm just kind of turning it into a formula instead of, you know, taking each polynomial as we go. So now let's think about this, right, this whole thing, my derivative, as a sigma notation. So writing that in terms of sigma, I can say I'm going to start off I equals 1 to n a sub I times I x to the I minus 1. And that gives me a formula for my derivative of my polynomial, right? Whereas if you remember, polynomial I equals 0 to the n a sub I x to the I, our derivative now, okay, I equals 1 to the n a sub I times I x to the I minus 1. So we've turned it into a formula. It's a shortcut, a way of writing things, so I don't have to you know, write it each time. All right. So you guys a chance to finish writing that. Then I'm going to go back over a couple examples that we did, I guess, early on in chapter 1 when we talked about like a spherical balloon with radius r and volume b when the volume was changing, right? We're doing the derivative of volume with respect to the radius, and then we'll take a look at that television. Remember we had that, you know, rectangular television where we changed the diameter size, you know, what was the rate of change of the area. So now we're going to do those things, but with our power rule. So example 4, spherical balloon with radius r. So remember our sphere, our radius r, right? So imagine, right, I've got this balloon and I'm, you know, blowing it up so the volume is changing, right? So the radius is changing, the volume is changing. We want to know what's the rate of change of this volume and radius, right? So what is the derivative of our volume with respect to the radius when the radius equals 5? So there's two different pieces here. One is I need to figure out what's my rate of change of my volume with respect to the radius. Once I figure out what my derivative is, then I'm going to plug in r equals 5 and see what I get. Okay, so dv dr when r equals 5. So I'll write it like that. That's my big question mark. Okay, so let's write things out. So dv dr equals 4/3 pi d dr r cubed. Okay, so this is with respect to the radius. So I'm looking at what's my, you know, I want to take the derivative with respect to r. So I'm going to take 4/3 pi r cubed, right, is my volume. So I'm doing it with respect to r. So I'm going to take the derivative of r cubed, right? So then this becomes dv. Yeah, this we're going to use our power rule. Okay, so it's a little easier. I don't have to do the limit like I did before. Dv dr of r cubed equals 3 r squared. Okay, so I take this and I'm going to plug it back into here. So this is equal to 4/3 pi times 3 r squared, right? The 3's are going to cancel. So I'm left with pi r squared, 4 pi r squared is my dv dr. Okay. My rate of change of my volume with respect to radius, okay, is 4 times pi times r squared. Okay, now we said when r equals 5, I'm going to plug that into here. So I'm going to get dv r equals 4 times pi times 5 squared. And I just multiply it out. So I got 100 pi. And this was in inches cubed per inch. Okay. All right. I left it in terms of pi. Leaving it in terms of pi is fine. You can multiply through if you want. Last time when we did this, we had to find the average rate of change. We had to come out, maybe take the limit as h goes to 0. So now we're using the power rule, so it's a little bit quicker for how we solve this. So the same thing, we're going back to an old example that we did at the beginning of chapter 1. So we've got our area as a function of the diagonal, 144 over 337 times d squared. D is our diagonal. So it's the IROC of the area, so a prime of d. I'm going to take my derivative with respect to d. So I've got my constant multiplier times, right, my power rule. So I'm going to go 2 times d to the 1. So then I just multiply it through. 2 times 144, right, divided by 337 times d, that's it. Okay. Okay. The power rule is a good shortcut, but really it's based on our definition of the derivative. Okay, so be very careful. Don't think it's magic comes and isn't a great thing. Why do we have to do the definition of the derivative? Power rule is the definition of the derivative. It's just that it's a shortcut. All right, so that was chapter 2.1. See how quick that was. I'll scan those in later, that lecture examples. All right. So I'm going to start chapter 2.2. We'll see how far we get. We've got about 15 minutes. So chapter 2.2. So these have the product and quotient rules. By the way, you guys can see chapter 2 homework is it's up on our campus page, although I believe the due date is set for next week. If you wanted to get a head start on it, you can. Okay, so let's talk about our product rule first. So our product rule says if our functions f and g are differentiable, okay, so in and of themselves, they're differentiable functions, then that means f times g is also differentiable. Okay, but the rule goes like this. So I've got f times g, and I want to take the derivative of that. Okay, so what happens is I'm going to take the first times the derivative of the second plus the second times the derivative of the first. And it doesn't matter if you do derivative of the first times the second plus the first times the derivative of the second. We're adding it, so it doesn't matter what order you go in. This is your product rule. Okay, what you may not do ever is take the derivative of one, derivative of the other, multiply it together. Can't do that. You have to do first times the derivative of the second plus the second times the derivative of the first. Okay? Sometimes I just write it. Okay. And this also comes from, this isn't just like magic too, this comes from our limit as h goes to 0, all these things, right? If I worked that whole through and I took the product of those, I would see this is what comes out of it, right? We can come out with the product rule, so I don't have to take the limit each time. But in the background, we're actually taking the limit as our secant line approaches our tangent line. Okay. All right, so let's work through some examples on these things here. All right, so we want to find the derivative of h. So I'm looking for h prime of x. I've got two functions, right? X squared, and then the other function is 9x plus 2. Now, I know you're thinking, well, why can't I just distribute x squared into both these terms and then take linearity and work it from there? You can, absolutely, okay? But we're talking about the product rule here. So we start off with function cases that are straightforward to work with and where you can see what the derivatives are, okay? So we're going to work with this one. So if you think about h prime of x, okay, So what I'm going to do is I'm going to say the first function, x squared, times the derivative of the second. 9x plus 2, I take that derivative, I just get 9. Plus the second, 9x plus 2, times the derivative of the first. And then that's it, right? I'm going to clean it up, right? So this is going to become 9x squared plus 18x squared plus 4x, which is equal to 27x squared plus 4x. Okay, both of these are correct, right? This looks nicer, right? When I look at that, it's easier to grade than if it was all left out like that. But when in doubt, right, you can leave it like that. Unless it says simplify and combine all like terms, you can actually technically leave it like that. Okay. All right, example number 2. My first function, my second function, okay? And again, like I said before, I can technically multiply all these out and then just do my power rule on all of those different terms, but we're trying to give examples for our product rule. Okay, so my y prime. Okay, so the first, 2 plus 1 over x. Right, now let's remember 1 over x is equal to x to the minus 1, just so we know. We got to take the derivative of that, okay? So 2 plus 1 over x times the derivative of the second. So 3 halves x to the, remember, 3 halves minus 1 is going to equal to 1. Okay, constant term becomes 0 plus my second function, 3 halves plus 1 times the derivative of the first. So I take the derivative of each term. Derivative of 2 is equal to 0 plus this derivative here. This is going to be equal to minus x to the minus 2. Right, by my power rule. I bring down the 1, so I get minus x, but I subtract 1 from my exponent here, so that's minus 2. Now I get to do all sorts of fun algebra stuff of combining all these like terms. Technically, this is my derivative, but I'm going to combine it just so you can see. So, I'm going to get 3x to the 1/2 plus 3 halves x to the minus 1, that's this term, times x to the 1/2, okay, plus this right here. So this is going to become x to the 3 halves plus 1 times minus x to the minus 2. I'm going to get to combine that in just a minute. We'll do these piece by piece. So 3x to the 1/2 minus 3 halves x to the minus 1/2. Why did I subtract that one? I think I must have combined it over here, yeah. Plus x to the minus 1/2 minus x to the minus 2. Okay. Need to think about why did I make that a negative. I think that should be, because I multiplied this by here, so that becomes negative over here, and then I was working with x to the minus 1, right? And then, yeah, so I just multiplied these out. Anyway, equals 3x to the 1/2 minus 1/2 x to the minus 1/2 minus x squared. Okay, technically speaking, you could have left it like this if you weren't sure, if you wanted to leave it, or you could combine like terms to get that. Okay. All right. Another example, t squared e to the t. We talked about the derivative of e to the t in the previous chapter section. So when we go to calculate that derivative, right, we're going to use the product rule, right, because our first function is t squared, our second function is e to the t. So we're going to say first, t squared times the derivative of the second, plus the second times the derivative of the first, 2 times t. Doesn't look like I'm taking the derivative, right? Because I'm just repeating it. But remember, our derivative of e to the t is e to the t. Okay, so now I get to combine like terms. So this becomes t squared e to the t plus e to the t, e to the t. Or I could just factor out an e to the t, t squared plus 2t. Or I could factor out a 2 times e to the t. T e to the t. Right, and then I'm going to get t plus 2. Any one of these is fine in terms of how you want to represent your derivative. They're all equal. Okay. These are probably easier to grade, but they're all equivalent. Okay. That's your product rule. Okay. So product rule, let's talk about quotient rule. I think we've got time to do, for me to introduce the quotient rule and maybe do one example, and then we'll quit for the day and we'll come back and practice some more. Okay, so quotient rule. So I've got my two functions, f and g. So if f and g are differentiable, okay, and then their quotient is also differentiable. All x except where g of x is equal to 0, right? So we have to take a look at, right? I can define this as differentiable, except I have to watch out for my divide by 0 errors. It's a rational function. I have to make sure that I'm including that domain problem. So it's going to be differentiable everywhere except wherever g of x gives us a 0 value. Okay, so let's talk about our, I've got f over g, and I want to take its derivative. Okay, so what we do is we say the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay. Order here is important because I'm subtracting, right? Bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. Write that down. Bottom times derivative top minus the top times derivative bottom all over. This is the function, the whole function, bottom squared. Okay. This is actually just a tweak on our product rule. Okay. So if this would be like f times g to the -1, my function, this is what I would get if I were to do out the product rule. Okay. So that's how we need to think about that. So we'll do a quick example and then we'll quit for the day. And then tomorrow we'll finish up 2.2 and then I'll answer questions on homework for 1.5 and 1.6 tomorrow. And then in addition to in the office hours, if you have questions on it, and then we'll break for our quiz tomorrow. Okay, so we've got this function x over 1 plus x squared, and we want to find its derivative. So, right, I've got a function over a function, which means I'm going to use the quotient rule. Okay. My quotient rule is going to go like this, right? I've got the bottom, 1 plus x squared, times the derivative of the top. That would be 1. Okay, the derivative of x is equal to 1, minus the top times the derivative of the bottom. 1 plus x squared, I go to take that derivative, I just get 2x. All over 1 plus x squared, squared, quantity squared. Okay, be careful, it's the whole quantity that gets squared. Okay, so now I can think about if I want to combine like terms. So I'm going to get 1 plus x squared minus 2 times x squared all over. And combine like terms, so this just becomes 1 minus x squared all over 1 plus x squared squared. And then that's it. Don't simplify it. I can't simplify it further. I'm going to leave it. Okay. We used our quotient rule. You may be asked to use the quotient rule specifically, to see if you know it. But if you can't remember the quotient rule, you can always bring this up so that this looks like x times 1 plus x squared to the -1. Okay. And then do the product rule. If you do the product rule on this, you're going to get the same answer. It might look slightly different because of the way that we're combining our terms here, but you should get your product rule. Okay. Unless you're told specifically to do the quotient rule, but it's helpful to remember it because it's just a much quicker way to get there. Okay, guys? But tomorrow we'll pick up with this, okay? And then we'll do the rest of the examples for chapter 2.2. And then, like I said, I'll go over homework problems for 1.5 and 1.6 tomorrow. And then we'll break for our quiz, okay? Bye, guys. I hope you have a great day.
Sorry, Professor, when are your office hours? I keep forgetting.
My office hours are from 1 to 2, And there's a
Okay.
Zoom link. The Zoom link is on our syllabus, also on our homepage for the office hours.
Great. Thank you so much.
Okay,
Thank
bye-bye.
you.
Take care.
Bye.
Thank you.
Bye-bye, guys. Take care.